Bismillahirrahmanirrahim. Okay, guys, we shall repeat this exercise because I have missed the one session for one group. So I shall repeat this exercise. Any of you can keep it as a reference, or you can come back to see how the approach to settle or to deal with the question like this. Okay, actually all the questions are the same in terms of the approach to solve the issues given. Okay, now we have a DC-DC converter. Even though for the time being you have not yet designed or have not yet come across the design of DC-DC converter, because this is the what's so called syllabus per previous semester, whereby we learn about the converter, then only we go in terms of their thermal consideration. But for this semester we learn thermal first, then only we go with the converter decision or converter design. Okay, howsoever, assume that I will discuss in terms of how we want to determine their voltage rating and their current rating, and to suit with the selection of the heatsink that appropriate for the design. Okay, so no need to be worried, because inside your test letter, because you have not yet come across converter design, so we give you directly in terms of their values. Amperes, how much amperes coming through your circuit, how much heatsink you have to provide to cool down the junction such that it does not increase or exceed certain limits. Okay, let's say we have this kind of question. Okay, we have this kind of question whereby we being issued with a circuit and the parameter that involved inside our circuit. So we have here the circuit of DC-DC converter. The input is 100 volt, you can see here, and the frequency that we trigger the switching, so this is your switch, it triggers here 40 kHz. As what we have mentioned before, this is the factor that will affect in terms of the capability of your switch. And even though it was stated inside at your front page how much the device or the part can withstand the current, see here, we have here 12 ampere, we have here 100 volt, but when involved in terms of the frequency operation, so you have to consider their limits. Okay, let's say we have this question. So what the first thing we need to do is that we draw the equivalent, also called thermal circuit. See here, we have two junctions here need to be considered, because we have two devices. One is our main switch, which is MOSFET. Another is our power diode. So the sequence that when we operate this circuit in the DC-DC converter, we are converting the 100 volt of input into a lower voltage of our output here due to switching. So we switch it on and off when we rectify, so it becomes a lower voltage level compared to 100 volt of incoming. Okay, so this is how we perform the switching. So switching, when we take average, so this is the output. Okay, maybe less than 100 volt, depends on the cycle that we apply. Okay, the first thing you have to do is that you have to consider two parts that are operating at this point, or in this part, or in this circuit, two main points. So during on state, so we have here on and off, 60% on, 40% off. Okay, that's why we have here 0.6. 0.6 duty cycle means that 60% on, 40% off, and it repeats again, and repeats. During positive cycle or during on cycle, the current will flow inside your MOSFET, return to your source, so 60%. During off cycle, so the remaining current that we pump inside our inductor here, we need some arrow or need some circuit to deplete. So if not, you cannot switch on your MOSFET because you have what's so called current that still remain inside your circuit, so it will create spark and backfire. So it needs some what's so called circuit to deplete the current. So that's why we have here power diode to deplete the current inside inductor. Deplete to 0, then the next cycle start, and only the next cycle safe to start. Okay, so on through the outer loop, off through the inner loop. Okay, so that is the process how the circuit is operating. Okay, then we have here two switch, MOSFET and diode. So we have to write or draw two main heat generation point, which is T junction of the MOSFET, T temperature junction of your rectifier. Or in other term, you can draw like this. So we have here TJ of our MOSFET, TJ of our rectifier. Then it combines into another, because if we have only one source, so if with heatsink, we shall have 3 elements. You see, 1, 2, 3. So 3 elements. Now we have 2 source with 1 heatsink. So this is common heatsink. Okay, it shows here we have the main with a common heatsink, means that both switch will be attached into one heatsink. Both switch will be attached into one heatsink. We have one heatsink. This is your heatsink. So this is your MOSFET 3-leg. This is your diode. So both are attached into one heatsink. So how the circuit will be looks like is you have 2 channel of or 2 source of heat junction. So you have another. So this is your R from junction to, this is your case, sorry, T case, junction to case. So this is your so draw properly, T case. So this is your T heatsink, TS. Meanwhile, because it shares the same heatsink, so this is your this is T ambient. This is your so okay. So this is your T ambient. So we be like this now, and like this. T case. This is the point. T case. T heatsink. They share the same heatsink. And this is your ambient. Okay, this is your TJ rectifier. This is R thermal, JC, R thermal, CS, the same R thermal, CS, R thermal, JC of the MOSFET of your rectifier. Nampak tak? So this is R thermal, SA of both part, because both part are planted or attached to the same heatsink. Okay. So complete the first step, which is you draw the circuit and equivalent thermal circuit. You can also draw like this, because we are considering your PD rectifier. Over here you can write or draw PD MOSFET. look at the question again. We have here two part number NTD 12 and 10 and BY 229. So we refer to the two data sheet. So we have here another information, which is the heatsink being provided with this value. So heatsink being provided. Okay. The question is that determine all operational powers and temperatures with the condition that TJ of your MOSFET should be operating at 100 degrees C. So other than all the information here that we have, and we put it inside our diagram. Right, so TA is how much is now? 50 degrees C and TA. So this is our T ambient 50 degrees C. Our thermal SA heatsink to ambient is 3 degrees C per watt. Degrees C per watt. So draw or write nicely. Yeah? Okay, what else we have here? TJ MOS should be 100 degrees C. T is temperature, degree C. R thermal is your thermal resistance. So degree C per watt. Okay, first what we need to do is that we settle one by one. So we look at our MOSFET, the main switch or the main part inside our converter. So we consider the MOSFET part first. So MOSFET, TJ of our MOSFET is equal to PD R thermal JC plus R thermal CS plus R thermal SA plus TA. Okay, so this is our MOSFET part. So means that the current will flow is the thermal will emit to your ambient through this line. We consider this loop first, then we consider this loop afterwards. Okay. Okay. Then, but at the same time, we can consider also the equation of your TJ for MOSFET is that PD R thermal JC junction to case plus TC and TC here and the same. This is the Ohm's law, the same. R thermal JC plus TC. Okay, now we take a look at our information that we have. It was stated that TJ we need to maintain at 100. So we have the information of 100 degrees C is equal to PD that should be limit at that value, which just to maintain TJ at 100 degrees C with R thermal JC. So R thermal JC is the information that we should get from the data sheet of our MOSFET, because we are dealing with MOSFET. So how to find R thermal JC? So when you look at your MOSFET here, look at your MOSFET. So it shows here in the page of maximum rating. If you can see the maximum rating, it shows here your limits of your thermal R thermal JC and JA. So JC is the values that we use when we apply that heatsink to the system. JA is the situation whereby we don't use any heatsink. So you take a look at your part here. This part we don't have any metal screw hole. So means that we either